Welcome back. We are doing thermodynamics homework solutions for thermodynamics 1. This is homework number 8, which is entropy analysis, feasibility, efficiency, that sort of thing. The first problem in the homework is out of Koretsky's textbook 3.26, second edition. And I've already started the problem. So basically what we have is we have a piston cylinder. It's got steam, and it's got a half kilogram of steam. It's isothermal, so it's 400 stays 400 K. It goes from 100 bar to 1 bar. Okay. And what we're trying to find is the maximum work possible. Did I get that right? Yeah, the maximum possible work and the entropy change of the surroundings. Okay. Entropy change of the surroundings is obviously associated with the heat transfer. Okay, so we're really trying to find W and Q. Simple as that. Okay, so I drew my picture, I drew my boundary. Let's make some assumptions. Okay, so we're going to assume it's isothermal. Okay. We're going to assume it's a closed system. Okay, there's no leaks. We're going to assume that there's no shaft work. Okay, there's boundary work, but there's no shaft work. We're going to assume that delta KE and delta PE are pretty much zero. Okay. Does it say? It does not say what the surrounding temperature is. So, however, to keep it isothermal, oh, sorry, that's not K, it's degree C. It's not K, right? Yeah, it's degree C. To keep it isothermal, usually what you have it in isn't you have it in a heat bath. You have it like in boiling water or something that's maintaining a temperature of 400 degrees Celsius. And so we can reasonably assume that the T surroundings in this case is 400 degrees Celsius. Okay. So and that's not a terrible assumption. Okay. In fact, that's really the only way that this is going to happen. And so there might be some other assumptions. Let's kind of work with those for now. So we drew a picture, we drew a boundary, we have our assumptions. What's next? That's right, we need a mole or mass balance. Now we have steam, so we want to use mass balance. So we have m dot I minus m dot E equals dm dt control volume. Okay, in exit. Okay, that goes to 0, that goes to 0. So dm dt control volume equals 0. That means that dm is equal to 0, which means m2 minus m1 is equal to 0, which means m2 minus equals m1, which equals m. Okay. Got that established. All right, now let's do our energy balance. That's right. Okay, so I'm gonna kind of erase this mass balance. That's not, it's obviously helpful, but it's not super helpful. I'll just remember that, the mass is constant. Okay? So we have m dot I hi plus 1/2 v squiggly squared I plus gzi in minus m dot E gze up. He plus 1/2 v squiggly squared E plus gze plus q dot plus work dot equals d capital U E K plus E P dt CV. Okay, nothing coming in, nothing coming out. We have heat, we have work, we don't have kinetic energy, and we don't have potential energy. Okay, we also don't care about time, this just happens, and so this is going to simplify down to Q plus work equals D capital U. Okay, now our capital U, we're going to write it this way. So we have Q plus work equals capital U2 minus capital U1, which equals M2 U2 minus M1 U1, which equals M of U2 minus U1. Okay. And so, okay. Now, I have enough to get this because I have a start and a finished state, and this is steam. What I don't know is I don't know the heat and I don't know the work. Okay. And so now I have to look at my entropy balance to get that. Okay. So let's erase most of this and then simplify it down to what we need. Okay. So we have Q plus work equals M U2 minus U1. And of course, you know, at T equals 400 and P equals 100, U equals something. Same thing at T equals 400 degrees Celsius, P equals 1 bar, U2 will equal something. Okay, so let's just assume we've looked those up, we have those. Okay, so now let's do our entropy balance. Okay, so we have S dot gen of the universe equals summation of exits, M dot SEE, minus sum of ins, M dot ISI, minus sum of all the sources of heat transfer divided by the surrounding temperatures, plus ds dt of the control volume. Okay, well there's nothing coming out, there's nothing coming in. Well, that's kind of, now, okay, we assume though, maximum work, meaning, you know, basically, so we're assuming maximum work, which translates to S dot gen is equal to 0. Okay. And we can write it either way, it doesn't matter, okay. So this goes to 0. So we're basically, excuse me, we're basing the analysis on, okay, I'm not generating any entropy, because if I generate entropy, this is not a reversible system, this is a irreversible system. Okay. So how does this simplify down? Okay, I've got, and again, I'm going to take away the time term, so I've got Q divided by T surroundings, and this is equal to capital DS, which is equal to M2 S2 minus M1 S1, which is equal to M delta S. Okay. So here I can also get S. Okay. So I've looked this up, I have this value. Okay, that equals my Q divided by T, you know, Q divided by T surroundings. Okay. And so this is my entropy generation of the surroundings. Okay. Or my entropy contribution to surroundings, whatever the question is truly asking. So I'm just solving for this and I plug and chug. Okay. And that's going to give me a certain number. Okay. Again, I'm using 400 degrees Celsius, but I do not use 400. I do not use 400. I do not use 400. Why? Because it needs to be an absolute temperature scale. It needs to be in Kelvin, so I should use 673.15. Okay, for this T surrounding right here. Okay. The only reason it's given in degrees Celsius is because that's what the tables are based on, and it's just easier that way. Okay. So now that we have a key, you know, Q divided by T surroundings, okay, well, I have a Q, and I have a T surroundings, and I have my energy balance, which was, you know, this guy up here. So now I have a Q, now I have an M, now I have a U2, now I have a U1, I can get my work. I mean, it's just algebra at that point. Okay. And so really the thing that sets this problem apart from what we've been doing with energy balance analysis is that quote-unquote maximum work possible. Okay, that us, you know, with everything the same, what's the maximum work? Okay, especially in this system where the pressure's changing, and so I can't just use a straight up PDV. I have to use my entropy balance to figure out my heat transfer, and then from my heat transfer and my, the difference between my two states, I can back calculate how much work I can get out of the system. Obviously, I'm never going to get that much work because I'm going to have irreversibilities like friction.